Okay, so our next topic is different algorithm, a different problem. The problem is interval scheduling. I'll first of all define it, and it's a greedy algorithm. So it's a greedy algorithm just like Prim's is a greedy algorithm. It takes a locally optimum decision. So it does not look at the overall picture, but at a given situation, it looks at the best possible situation in the local situation and takes a decision. And surprisingly, it always gets an accurate result. Okay, so what is interval scheduling? So in interval scheduling, we have a number of intervals. So S1 is the starting point. Okay, so let's imagine that this lecture hall, a number of teachers want to use this lecture hall, for example, say their makeup classes. Okay, so every teacher will send a request to ACB that kindly arrange my makeup class on Saturday. ACB will try to facilitate the maximum possible teachers, but it cannot allocate two people the room at the same time. Okay? So that's the constraint. Similarly, a laptop can be given to somebody, but it cannot be given to two people at the same time. Okay? So we want to make everybody happy, like the maximum people happy, without violating the condition that no two people can share the resource. So the problem can be applied to a lecture hall, a computer or a server, or for example some electronic microscope, atomic microscope that a number of researchers want to use. So any resource that multiple people want to use from a start time to a finish time. So every teacher or every person will send a request. Each request will consist of two things, just two things, start time and finish time. So this is the start time and finish time of the first request. This is the start time and the finish time of the second request, and so on. We have n requests. So n people have requested and said that we want this lecture hall for this start time till this start time. Okay. And the goal is to find the maximum number of requests that do not overlap with each other, because the same laptop or the same lecture hall cannot be used by two people at the same time. So that's the condition. So an example is that a person, for example me, wants to use this lecture hall from 8 to 5, from morning to 5 o'clock. So we can represent this thing with a line. So this is the 8 o'clock, this is the 5 o'clock, and it's a long interval because it occupies the whole day or most of the day. Then the other request is just for 1 hour from 11 to 12 o'clock. So this can be pictorially represented as something like this. And the other is from 3 to 5, so this can be pictorially represented like this approximately. And the problem that we want to solve is what is the maximum request that we can accept? Two. So essentially what we need to do is drop this long person, so we'll make one person unhappy but make two people happy. So it's a democratic algorithm, so it treats everybody equally. Okay? It doesn't differentiate who's rich, who's poor, who's senior, who's not senior, and so on. If you want an undemocratic system in which you give certain people priority, say how much money they pay, and then you give them. So for that, there's another problem called weighted interval scheduling. So you kind of, every person says, I will need this thing from this time to this time, and I am paying this thing. So now I'm optimizing my profit. I'm not trying to make maximum people happy. So we will drop this request, accept the other two, and this will be our solution. So the generic algorithm, just like the minimum spanning algorithm, is a greedy algorithm, and it has a generic algorithmic form. It's not a concrete algorithm, so it cannot be directly implemented. There are some missing parts. So initially the set of accepted request is empty. So A is the calculations that our algorithm is performing. It's initially empty. And then there will be a loop, like many of our algorithms, that will check if there are requests in R. So we have R, we will take out requests from R until the R is finished. Okay? So we will select a request according to a strategy, any strategy. So we will select a request according to some strategy R, and we don't know what strategy we will be using, and then we will combine it with the already calculated answer. And when we include R, we need to remove all requests that overlap with it. Why do we need that? Yeah. So for example, if I accept this one, so I have to disregard this one because it's overlapping. But this one is fine because it's not overlapping. Okay. So we remove all these. So the one thing that we haven't studied is what do we mean by greedy strategy, and we need to define what we mean by a greedy strategy. There can be many greedy strategy, and I can be greedy for money, I can be greedy for fame, I can be greedy for cars or whatever. So there are many greedy strategies, not all will work. In fact, for most of the problem, there is not a single greedy strategy that will always work. So remember this thing, we are looking for a greedy strategy that no matter what the input is, it will calculate the correct optimum number of requests that can be accepted for the given input. Okay? So for a given input, it will always calculate the optimum results, just like a human can do. Okay? So, in order to show that a strategy is correct, we need a formal proof. We need some reasoning why it is always correct. Okay? But to show that a strategy will not work, we need just one counter example. Okay? So even if we have one counter example, we will know that this strategy will not work in this given situation, And since we want a strategy that will work in all possible scenarios, we'll disregard that strategy because we are looking at algorithms that always work. So just like a simple thing, we don't need a sorting algorithm that sorts some input arrays but is unable to correctly sort some other input arrays. So this way we want an algorithm that optimally computes the optimum number of strategies. So what is a counterexample? What is a counterexample? So any case in which our idea is not working. So for example, a counterexample is a specific example in which a proposition in which an idea is not working. So it's false. So an example can be, I can propose that the sum of two even numbers is false, and this is an easy proposition for which we can make a counterexample. What can be the counterexample in Imranullah? So we are saying that we pick two numbers that both are even, we add them, the resulting number will be odd. Which is not right. So we need a counterexample. So we can pick any two even numbers, 8, and since this is even, so this is our